Today, I will introduce complex Fourier series. Before this video, I've introduced real Fourier series. However, in application like physics, we usually use complex Fourier series because it makes the computation more elegant. So we first define what complex triple series first. So given Cn and n runs from negative infinity to positive infinity, which is a bisequence of complex number. And what is a bisequence of complex number? Well, it is a map from Z to C. The triple series associated with it is given by limit as n tends to infinity Cn e to the inx, and we run the index from negative n to n. And we define it as replacing this n by infinity. And this is just a definition here. And we restrict our x in the closed interval negative pi to pi. And we can also define what a complex Fourier series is. Given a f which is integrable on the interval negative pi to pi, we can define the Fourier series by the same expression as the triple series, but with the special type of coefficient. And the coefficient is given by 1 over 2 pi times the fx times e to the negative inx, and we integrate from negative pi to pi. So, what is the complex integration? Well, I will recall this. Given a complex function defined on the interval ab, the integral is defined as the integral of the real part plus I times the integral of the imaginary part. And what is the motivation? Well, the motivation is very similar to the real one. And we just apply the integral formula here. And I will leave it for you to verify it. So, how can we relate the real Fourier series and the complex Fourier series? In fact, we can relate it. First of all, as Cn is defined as 1 over 2 pi times this expression, we simply multiply 2 pi to left hand side, and we get that 2 pi times Cn is equal to fx e to the negative inx, and you integrate from negative pi to pi. And from the Euler's formula, we see that this expression cosine nx minus sine nx is equal to e to the negative inx. And the next step is to apply the definition for the complex integration. And we divide it into the integral of the real part and the integral of the imaginary part. Well, observe something. The left hand side here is equal to the pi times an, where an is the coefficient of cosine nx for the real Fourier series. And for the right hand side here, it is equal to the pi times the bn, where bn is the coefficient of sine nx in the real Fourier series. So, if we cancel the pi at the both sides and we divide 2 to the right hand side, we get that Cn should be equal to 1/2 times an minus ibn. And for the zeroth term, we see that C0 should be equal to B0. The reason is that when n is equal to 0, e to the negative inx is equal to 1. So C0 is the same expression as B0 in the real Fourier series. And how about for n smaller than or equal to negative 1? We see that for n smaller than or equal to negative 1, Cn is equal to 1/2 times the a to the a negative n plus I b negative n. And I will leave it as an exercise for you to verify it. So, comparing the coefficient in the for the negative index and the positive index, we see that we have this relation. This relation is c to the negative n is equal to the conjugate of Cn. And so, we see that if f is a real value function, then the coefficient in the complex Fourier series satisfies the relation that the negative index of the complex Fourier series coefficient should be equal to the conjugate of the coefficient with positive index. And this is the end of the video about complex Fourier series, and we will continue in the next video. See you in the next video.